Yeah, I'm gonna try this. Boom, the audio just cut out. So I'm not sure. I should be preparing the example here. Yeah. So we're doing an example where the objective is to find the the extrema of this function f over the domain that the problem specifies. Can I kind of, well, just let it go. So here's the domain that the problem gives us. And there's going to be these two steps that we've got to do to complete this problem, right? So I'm going to start drawing a picture here in a second. And the point of the picture is to highlight in parts first what we do on the interior of the domain, and then afterwards what we do on the edges of the domain. So we had written out a sequence of steps last lecture. The first steps were to find the critical points on the interior, collect those values, and then check the edges. So here I'm making a sketch of a rectangular domain. It's got four edges. And on blue in a second, I'm going to draw an example of the some values of the function on these edges. So on the right edge, it might look something like this here. On the left edge, here's another example. Note that I drew this one to have a little minimum on it so that we might have to consider that point. That was the bottom edge. Sorry, here's the left edge here. And then we just fill in some other behavior for the top edge. So all of that is boundary behavior. That has nothing to do with the critical points on the interior. We will have to devise a method to check um, what the extreme values are on all of these edges. So here I'm drawing in red dots, like these are all the relevant locations. Every corner, every little local maximum, local minimum. In theory, these all have to be checked. So technically, that's the second part of the set of steps we're going to do. The first part I'm going to try to highlight now. So here I'm trying to make some kind of a sketch of some interior behavior. We make it a little mountainous. I wonder if I'm stuck here trying to decide what to draw next. Uh, no. Yeah, I think I'm rambling about the interior here, but okay, there we go. We continue to draw. So what's in gold is like this mountainous region over the purple domain, and you can see I've drawn it in such a way that go back to the red. There's a couple relevant points. That's a critical point. That's a critical point. And so in the case of this exact picture, that one might be the absolute maximum. But in general, what the strategy is, I'm going to start skipping this video. And I see 30 seconds is too much, though. Can I do a little bit? Okay, here I'm highlighting that value on the z-axis. Every single one of these red dots here corresponds to a value on the z-axis, we don't care whether the red dot is found on the boundary or the interior. We only care about what its value is. So this red dot here is as big as it gets on the interior. This red dot here is as small as it gets on the interior. But then all of these exterior dots, right? So this calculate the max and min on the boundary. We're going to have to find a different technique for evaluating those. But at the end of the day, there's just pause. At the end of the day, all of those red dots have to also be thrown into the mix. Let me just try to jump ahead here. Yeah, see, so I've drawn all the dots in. So all of those red dots correspond to values on the boundary here. And when we go to find those red dots, this is going to be reduced to some one variable calculus stuff. We'll see that in an example in a second. And then that's the point here. There's there's an absolute maximum and an absolute minimum, and they'll simply be the biggest number we find and the smallest number we find. So let's jump ahead a bit. Okay, so after the sketch I've given here where I try to get you to visualize what we're going to do in pieces, there's the gold interior. This is handled by using critical points in multivariable calculus. And then there's the blue part where we're going to do one variable calculus. We jump into the example. So to start, we're doing the interior. We need to find places where the gradient is 0. That's the same as simultaneously solving these two equations. This gold sketch here is actually not a sketch of the function that we've got here. It's just a sketch for intuition. So if we go to solve these two equations simultaneously, they reduce to the two that you see here. If you take the second line, take the first line and probably subtract the second line from it. See if that's what I do. Freeze. Yeah, you take the first line, you subtract the second line, you get this equation here, you solve for y. Y is 1. That forces x to be -1. And this is the only critical point on the interior. So for this specific problem, the first part is really easy. We find just this one critical point. We need to know what the value of the function is at this point because, right, when we have all those little red dots over there, well, the value of the function at this point is one of those red dots. We need to record this information. Here, I probably just did it in my head. It's all a bunch of ones and -1s. So you just plug in -1 and 1 everywhere. Comes out to be 33. And that concludes the first part. So we're going to have to jump to the second part. Yeah. So let me just pause here. Or maybe the drawing will work, but so here I'm checking the left edge of the domain. On the left edge, x has to equal 0. So it's kind of, you can imagine like that blue left edge over here. And if x equals 0, then the function f reduces to a function just of y. Because you can plug in x equals 0 everywhere and it'll get rid of all of the x's. So that's what you see me doing down here. Right, you plug in 0 for x everywhere, it reduces to a function just of y. And we really only care about y between 0 and 2 because the rectangle, the values of y are only between 0 and 2. So let me just pause here again. This right here now, this is a one variable problem. You have a function of y on an interval, and this reduces to calculus 1. Trying to optimize this function. So how do you do that? Well, you solve g prime of y equals 0, right? Wherever the derivative is 0. So that's what you see me doing here. The value 1/4 is in the interval from 0 to 2. So you do have to consider that point. If you had gotten like 5 or 30, that's not in the interval, we would ignore it. It is in the interval, so we record the value of the function. So here you can see I'm plugging in 1/4 everywhere to see what the function comes out to be. So that's another red dot for us. 23 and 3/4. We've got 33 up here. We've got 23 and 3/4 there. That's 2 red dots. You might recall from Calculus 1, you've also got to check the edges. So the left edge of the interval is y equals 0. The right edge is y equals 2. So each of those is a corner on the original domain. That gives us 2 more red dots, 24 and 36. I'm probably going to draw that in a second. I'm going to indicate it here. Right, so we've checked the bottom edge, this top edge, and this one minimum occurring in the middle. Not really the middle, but somewhere on that interval. So that's that edge. Now I'm going to jump ahead to the next edge. Boom, let's pause there. So here I'm trying to check the top edge now. For the top edge, I guess I can let it play. Y is fixed at 2. And that means that the function f reduces to a function only of x. You plug in 2 for y everywhere. And now you only have things involving x. There's a little typo. I'm going to fix that in a second. That should be an x right there. Let me just jump ahead to after I've corrected that. Yeah, I see I've corrected it. Okay. So let me just freeze here. If you plug in y equals 2 everywhere, this reduces to a function only of x. And you're on the intervals 0 to 4. Calculus 1, maximum, minimum. Set the derivative equal to 0. You get x equals 4. That's one of the edges. We're going to check that point anyways. So we got to check the left edge where x equals 0. The right edge where x equals 4. This is 2 more red dots. You plug in 0 to this function up here, and you get 36. If you plug in 4, I'm probably doing it in my head as I go through, but you get a lot of 16s, right? 16 minus 16 plus 16 minus 16. It just comes out to be 20. So that's the left and right edge of that interval. Now, let's see. Okay, so I've got to pick another edge. We're doing y equals 0, so this is the bottom edge now. You plug in y equals 0 everywhere, and the function f reduces to this function here, x squared minus 4x plus 24. Still, x is, between 0 and 4. Optimizing on that interval, you've got to set the derivative equal to 0, same as always. We find this one point, x equals 2. We also have to check x equals 0 and x equals 4 because those are the edges. So we got 3 more values. 24, 20, and 24. That's the end of the bottom edge. Let's jump ahead a little bit. Now here we're checking the last edge. This is where x equals 4, right? It's the right edge, like right over here. You plug in x equals 4 everywhere to the original function. It'll reduce to what I'm writing out here, g of y. So again, it's a function of only y, and now it's y between 0 and 2 again. And this is the last time we do this. We just check where the derivative is 0. 8y minus 10 equals 0. It's the same as y equals 5/4. We don't really need to check the 2 edges of this one because we've already checked those corners on the previous edges. So here we just check this one interior point. Plugging in 5/4 everywhere is a little bit annoying, right? Just because 5/4 is a somewhat of an annoying fraction. I think I'm checking it right now because I wanted to make sure I didn't make any mistakes. But yeah, here I'm plugging in 5/4. Excuse me. And this comes out to be something less than 20. So this is actually the absolute minimum here. Okay, so I hope we should zoom out now. We've got a lot of different points we just found, right? These are all different extreme values or candidates for extreme values. So on the interior, we found 1 point, right? It was at 33. And then we checked all these edges and look at all these values we got 23 and 3/4, 24, 36, 36, 20. Come on, let's get the rest of them. 24, 20, 24. And that last guy, 17 and 3/4. So the biggest of those three numbers, of all those numbers, is 36. And the smallest one is 17 and 3/4. So you just make a note of this somewhere. Like your final answer is an absolute maximum and an absolute minimum. So you just note this. So here we're just writing it out. Okay, so now I'm starting this next section. So that whole example was the conclusion of 4.7. Now the Lagrange multiplier section is kind of short. It's the conclusion of this whole chapter, 4.8. So here I'm starting it. And I'll hopefully start drawing a picture in a second. What am I talking about? Oh, I remember what it was. I was looking at the chapter and I was unclear as to why they were doing something in a certain order, and I was explaining that. Okay, so there is a function here. This is a function they give us. Let me just try to jump ahead a little bit. Here I'm trying to draw out level sets of this function f. So in red, we're kind of the lowest, right? This function gets bigger as we go away from its minimum. It's an upward facing paraboloid. So as we go from red to blue, the values of the function increase. And there's a minimum. It's the only minimum for this function. Right there, right in the middle. So if you were just asked to find the absolute minimum of this function, you would find the value of the function at that exact point and really nowhere else. So here's a different perspective on that same thing. Let me just jump ahead a little. Yeah, boom. Okay, so this is my upward facing elliptical paraboloid. Its level sets are what we drew over here on the left. And the technique for finding that minimum is you guys already know this. You solve grad f equals 0, and you'll find the x and y coordinates of that point. That's not my firearm. That's somebody outside. Okay, now here. No, jump ahead again. Okay, there we go. Freeze. Okay. For Lagrange multipliers, the goal is no longer to find the maximum or the minimum of a function, anywhere over the whole domain, but instead it's to fix a line. So this green line in the left picture here is the same as this blue line in the right picture. And to say you have to stay on this line. You're not allowed to leave this line. So let's see if I drew. Yeah, so here you can see on the right, I'm trying to draw that second blue curve there. This is what the function looks like if we're stuck on that blue line. You're not allowed to deviate, to exit the line. This point can't be the minimum anymore. It's not on the line. It's out of bounds. It's not allowed. So there's a new minimum. It's the best we can do if we have to live on the line. And it's right there. I just drew it in blue. Probably going to draw it in a different color now. Yeah, that little red dot right there. So it's not really the real minimum of the function. It's the minimum given that you have to live on the constraint line. We call these things we call them constraints. So there's an issue here. Let's see. Am I going to try and do this right now? Yeah. So here we write out a function describing that green line. This is a linear function. You set it equal to, I think, 216. And you'll get this green line on the left here. So let me pause again. We've got two functions in play. The function we want to optimize is the one we care about, f. And the second one is, they call it a constraint function. It's fixed. So in our case here, it's equal to 216. So there's a constraint function and a function that we want to optimize. So I think here we're just writing out the challenge explicitly. We want to minimize the function f. Let me just write it out and then pause it. Put the k in there. Yeah, this is the goal right here. We're trying to minimize a function subject to a constraint. And the constraint is always of the form, some function has to equal some constant. So g has to equal k, for instance. G has to come out to be k. Now something is going to happen, and I think I'm going to try to draw it right now. And this is the heart of the idea or the insight with Lagrange multipliers is, in theory, G has lots of level sets, right? G doesn't have to equal 216. It can equal 217, 218, 200, 100, 300. And so G has lots of level sets. And here I'm going to try to draw a few of them. So these are supposed to be parallel lines. And those are the level sets of G. And we've already got the level sets of F drawn in. And you might want to think about what is about to come up. This is the insight right here. If you're at a minimum or a maximum for the function F, it has to be a point where these two level sets are tangent to one another. They just kiss. And if the level sets of two functions just kiss like that, here I'm drawing in the gradient of G, has to be perpendicular to the level set of G. Here I'm drawing in the gradient of F. It's got to be perpendicular to the level set of F. What's true about these two gradients? Do they have to be equal? No. They have to be parallel. They can point in the same direction. They can point in opposite directions. They can be roughly the same size. They can be very different in size, but they must be parallel because their tangent lines, or no, sorry, their level sets, or their tangent lines, honestly, at that to the level sets, their level sets are tangent. So this is the whole insight of Lagrange multipliers. If you have a constraint G, you must live on the line, G equals K. And you minimize the function F, The gradients of these two functions must be parallel to one another. I'm going to try to jump ahead and see if I write this out now. Yeah, so here's the method. I'm going to write it out nice and clean. This method only works if f and g have continuous partial derivatives, but this whole course is about functions that have continuous partial derivatives. But don't worry too much about this detail. So you've got these two functions, and one of them is your constraint function, and it must be set equal to something. When they write it out, they say 0. It doesn't have to be 0. Any number k is fine, but they put 0. Now suppose you're at a point suppose you are at a point where f has a local extremum on the constraint line, right? So like that purple dot I drew previously. If you are at a point, x initial, y initial, where f has local extremum, basically what I'm about to say is that the two gradients have to be parallel. So the gradient of g can't be 0, but it won't be for any of the problems you guys have to do. But you need the gradient of g to be non-zero so it can be parallel to the gradient of f, right? If it's 0, it's not really parallel to anything. So lambda is they call this the Lagrange multiplier. This is the number. Here, I'm going to write it out right here. Relating grad f to grad g. So if two vectors are parallel, then they're scalar multiples of one another. So lambda is called the Lagrange multiplier. So there is some number lambda such that the gradient of f is equal to lambda times the gradient of g. That is the whole insight right there. Let's jump ahead. I'm not really sure what I'm saying here. All right, example. So for all of these examples, uh, you're going to be given a function that you want to optimize. Let's get this go a little farther ahead. And a constraint. You'll always start by writing out this equation here, grad f equals lambda grad g. You're going to solve this equation, and that's going to be how you find that x initial, y initial point, or those points, let's say. Where the two gradients are parallel. So it's not really one equation. Grad f equals lambda grad g is really two equations, right? The first derivatives in the x direction have to differ by lambda, by a factor of lambda. And similarly for the derivatives in the y direction. Let's write those out. Is the derivative in the x direction of f. This has to come out to be the derivative in the x direction of g, which is just 3, times some number lambda. We don't know what that number lambda is, which means we have 3 variables, by the way, right? X and y and lambda. Come on, Mike. All right, let's pause there for a second. Then there's the same thing for the derivative in the y direction of f. It's got to equal lambda times the derivative in the y direction of g. And then the constraint function, 3x plus 4y equals 32, that's our third equation. We need 3 equations because we have 3 unknowns. if we can solve all of these, we're going to have an X, a Y, and a lambda, at least one triplet. And that's going to tell us where our extreme values are. So there's a bit of work. These are kind of complicated equations, right? You see the 18s and the 36s and the 8s. So the first thing I'm going to do is divide those numbers away to get something simpler. Oh, no, sorry. First, take the third equation and solve for y, right? Just get that out of the way. That's easy. And then, yeah, here, divide in the first equation, divide by 36, just to get easier numbers. Here, I'm simplifying. So that's one of our equations. And the second equation, divide by 8. So we have just y. Let's try to jump ahead a little bit. So here now, if you divide 36 by 8, 8 by 8, 8 by 8, and 4 by 8, you get these numbers. Right? You get just y, but we plug in y equals 8 minus 3/4 x. So this right here is minus y. We simplify, we get this right here. We've eliminated y in both places. So now it's just two equations and two unknowns, x and lambda. Now I'm multiplying by 4 to solve for x. The bottom one, I'm also multiplying by 4. I want to solve for x. Jump a little bit ahead. X equals 30 minus lambda over 3. Plug that in for x in the second equation. Now it's just an equation in lambda. We can solve for lambda. Because that'd be 24. Right, 90 minus 18 is 72. Yeah. Lambda equals 24. We can solve for x. X comes out to be 22. And then what am I doing? Yeah, we're plugging in x right here. If x is 22, minus 3/4 x is minus 16 and a half. And I'll just say this. So here's our critical point here. I'm going to pause the video here. After all of that work, all of that algebra, we end up with this point. It's the only critical point. This is the value you're looking for. I'm not going to go further with the video here because if you can actually hear the original audio, I kind of lose my place. And let me just jump ahead a little bit, see if I draw it. Where is it? Come on. One second. Okay, right here. It's a little messy, but the constraint that they gave us is a straight line, this red line here. And the extreme value we found, 22, negative 17/2, that point corresponds to this extreme value. It's a minimum, but the way that we find out that it's a minimum is we have to say, well, what is the limit in each direction on this constraint line? And in both directions, it blows up to infinity. And because of that, we know this is a minimum. I'm not going to put a problem on the midterm with a straight line like this because I don't want you to have to take these limits. It's kind of a side issue. I only want you to have to find these critical points. So what I wrote here is just a little note for you guys. For the midterm, you only have to find the critical points, not classify them, because for right now, I don't want to go over finding these limits because it's peripheral to the goal of solving for these points. The only point you find using Lagrange multipliers is this point, and in the end, it gives this value f of 22 comma negative 17/2 as a minimum, but you don't have to go that far. You only have to find the critical point. So I'll stop the video here. I'll make an announcement about this on Canvas. I apologize again for the audio crapping out on the first round. I still don't know why that happened, but yeah. And so what I'm going to do is I'm going to postpone the deadline for the midterm by a day so that everybody has an extra 24 hours to work on it to make up for this error here. Along with that, if you have any questions, please email me. I'm around all weekend, so if you do have any questions, I'll try to respond as quickly as I can. And good luck on the midterm.